Yeah, okay, it is working fine. Uh, yeah, so for now, you can show that this is a Boolean ring. The set of all power sets, I mean, set of all subsets of natural number is a Boolean ring, and it is an infinite set, right? Of course, you have infinitely many subsets of natural number, right? This is one example of an infinite Boolean ring. Uh, okay, so now next question. Let R be a ring. You know, right? R cross R is a ring, is also a ring. Ring with like pointwise addition and multiplication, right? I mean, how are they defined? The element A comma B belongs to R cross R, let's say, and also C comma D belongs to R cross R. Then you define the addition of these two elements as the addition in the individual I mean, components, and multiplication in the individual components. This is the addition and multiplication of the ring. But how about now I generalize this concept? Let I be an indexing set and Ri, okay, be ring for every I in the indexing set I. Then show that product I belongs to capital I Ri is also a ring. So this is a very abstract way of defining a Cartesian product. Okay, a Cartesian product is simply product of R over n times. Right, you do it n times. That's your Cartesian product. I can generalize this Cartesian product for any indexing set I. Right. Well, how is it defined? Simply, the Cartesian product I belongs to I is the set of all mappings F from this indexing set I to union Ri, the property that F at any index I belongs to the ring Ri. Okay, this is a very abstract notion of Cartesian product, and what you have to show right now is if each Ri is a ring, then the Cartesian product is also a ring. Okay. Okay. So let's show this. Proof. Okay. I want to show that that is a ring, right? So first of all, it has to be a group under addition, right? So let F comma G are the two elements in product Ri, right? How is the addition defined? It's a point of addition. So F plus G at any element I is Fi plus Gi, and you know by the property Fi belongs to Ri, also Gi belongs to Ri, and since Ri is a ring, this addition operation is the operation in the ring Ri, and hence this guy again belongs to Ri, right? So addition operation is well defined. So this is a very abstract notion. So you can see you can really you have to relate everything to the natural Cartesian products, you know, Rn's, right? So if I do the addition in the first components, I mean you are doing in R1 in some sense. Okay. So F plus G is in Ri. So it is a closed. The operation is closed. under addition, and of course since it is component wise addition, f plus g is same as g plus f, not a component wise addition. Since each ri are ring, so the operation addition in each I is abelian operation. Okay, and you have this also. So what is the zero element, right? So you need an element 0 such that f plus 0 is 0, right? So you choose a function 0 theta, I'll call it, belongs to Ri such that theta of any element I is 0. Okay, what is this 0? 0 I, I'll call it, is the 0 in the ring Ri. Okay, so now then what happens if I add it with any element of the set? F plus theta at any element I equals to f at I, this addition operation of I, and then theta of I, right? But what is this? F at I plus this is 0, right, which is f at I, right, which implies f plus theta is same as f for every f belongs to the Cartesian product. Hence theta is the additive identity. Okay, now do I have the additive inverse for every element, right? Maybe I shouldn't partition the page, I just write on it. Now let an element f belongs to this product. Define g and g of any element I is minus f at I, right? Since f of I belongs to R is a ring, minus f of I is there. There is an additive inverse for every element in a ring. This guy also belongs to Ri, right? So this g is well defined. So what happens for f plus g? F plus g at I is simply f of I minus again f of I, which is 0. Which implies g is the additive inverse of f, right? So for every element f in product, you have an inverse also in f. You have additive, we have additive identity also, and the operation is closed. The operation is commutative, right? Hence, this is a group right now. I haven't defined what a multiplication is. This is right now a group. So now define product as f dot g at any element I is, yeah, the component based product f of I dot g of I. Since fi is in Ri, gi is in Ri, their product is also in, will be in Ri, because Ri is a ring. So this is in Ri, right? This is a well-defined product, and you can easily verify that this product is associative, since each ring Ri, in each ring Ri, the product is associative. Associative, hence this. Also the other properties of the dot product. I mean this product rule. Hence this Ri, I belongs to I, is a ring. Okay, so I have generalized the concept of Cartesian products Rn to any abstract set theoretic product. Okay, each Ri is a ring, imply the product Ri will also be a ring. Okay? If anyone has any doubt in this process, you can ask. I can re-explain it again. Okay, if no doubt, we can go ahead. So next question is, okay, so these are the ways to generate more rings from the given ring. I mean, I have known the rings Ri's. Let's say I created the whole product ring, right? Product Ri. Now suppose I have another ring. Let A be a commutative ring with unity. How can I go more further? Define R to be set of all functions f from A to A such that f is group homomorphism. Okay. Since my A was a commutative ring with unity, it is naturally a abelian group, right? So I can define group homomorphisms there. So if I collect all group homomorphisms, okay, this will form a ring with component-wise addition and multiplication as the composition operation. Okay. What are the operations? F plus G at any element, let's say small a, is Fa plus Ga, and what is F dot G at any element A is now F of Ga. Okay, this is different than the product. Okay, keep in mind this is a function composition. Naturally, we define the dot product in case of functional spaces as the product one, right? The point-wise product. This is not the point-wise product. This is the function composition. Okay, so I have to prove that yeah, the claim is show that R is ring with unity. I mean, unity is simply multiplicative identity, and the question is, what are the units? What are the units in this space R? We'll try to see. First thing is, we'll show that R is a ring. So if f comma g belongs to R, which implies f comma g are from A to A homomorphisms, group homomorphisms, what happens to f plus j? F plus j at an element, let's say A plus B. Okay, what I know it, this is f at A plus B plus j at A plus B, which is, since f is a group homomorphism, this is f at A plus f at B plus this is j at A plus j at B. Now I can recombine it as f plus g at A plus f plus g at B, right? So now you can see f plus g at A plus B is f plus g at A plus f plus g at B, right? I'm just using the definition of what a group homomorphism is. This implies f plus g is also a group homomorphism. Hence, f plus g also belongs to R, right? Now, what I want to show is it has the zero element. I have showed the addition is, I mean the, I have showed that set is closed under addition. Now I have to find a zero element. See, every element going to the zero element of the group is naturally a group homomorphism, right? Like theta, a map from A to A, so that theta of any element A is zero of the group, right? This zero is the additive identity, right? So this theta is a group homomorphism. Hence this theta belongs to your ring R. And now if you add any element with theta, what happens? You have Fa plus theta A, but since theta A is 0, you get Fa. So you have a additive identity in the ring R, and similarly you can define additive inverse also, like I define minus F at any element A is minus of Fa, right? See, Fa is an element of A, right? And hence there exists an inverse, additive inverse, and this is a well-defined group homomorphism, which implies F plus minus F at any element A is 0, which implies you have additive inverse, you have additive identity, your operation is closed under addition, it is a commutative operation, which implies R with this functional composition is a group. Now what happens to the multiplication? If I multiply two elements, okay, A plus B, what I get? I get F at G of A plus B, right? But since G was a homomorphism, I can write this at GA plus GB. Now since F again is a homomorphism, I can write this as F of GA plus F of GB, right? What is this? This is simply, okay, I have, what do I have at the left side? I have F dot G at A plus B. F dot G at A plus B equals to F dot G at A plus F dot G at B, which implies Fj is again a group homomorphism. Implies this dot operation is closed is a binary operation basically. Yeah, and you can verify the other properties, the distributive law. Okay, so this will imply that R addition and this dot is a ring. In fact, commutative ring. No, is it a commutative ring? No, is a ring. Now, does it have an identity element? So what that means, I need an element like 1 in some sense, so that Fj of A is equals to Fa, right? So what is F of any element? F this is same as F at this one function at A, right? So if I define a constant map 1 from A to A as 1 of an element A is itself, yeah, the identity map. And this is a group homomorphism. Hence, this identity map belongs to your ring R, which implies this identity map is the multiplicative identity. That's all. Then this will implies R plus dot is a ring with unity. Okay. So now, what are the units of this ring? Right? Units means the elements which has the multiplicative inverse. Okay. Right. So let F be a unit, then there exists an element G belongs to R such that F dot G is equals to the multiplicative identity 1, which implies F composition with G of A is equals to A for every A belongs to capital A, right? But when this is true, yeah, this is true if and only if, what do you say? I mean, F is bijective, right? then only you get an inverse. Right? I mean, this G is kind of a function inverse, right? Function inverse of f. This implies only if f is bijective. And f is already a homomorphism, right? This implies, this is if and only if actually, f is an automorphism. Right? Automorphism is basically bijective homomorphism from a set to itself. Right? So units of R is the collection of all functions from A to A such that f is an automorphism. Okay, this is about R. So, any doubt in this so far? If you have any doubt, you can ask, okay? Okay, if no doubts, we can proceed. Now there's another interesting question. You are familiar with integral domains, also you are familiar with fields, right? I mean, uh, any commutative ring with unity, which is an integral domain, such that every non-zero element is a unit, then the ring is called as a field. Okay. If every non-zero element has a multiplicative inverse in a commutative ring with unity, then you call it as a field. Okay. So now question is, show that any finite integral domain is a field. How do you show this? I'm going to take this to another page. Yeah. So that any finite integral domain is a field. Okay. So let's start with any non-zero element. Consider the map phi from R to R as phi of any element x is Ax. Okay, this is a well-defined map, and since R is an integral domain, this phi will be injective, right? How does this follow? Let's see. If phi x equals to phi y, then this will imply Ax equals to Ay, because this is the mapping, which implies A times x minus y is 0. But since A is non-zero and R is an integral domain which implies x minus y is 0, this will imply x equals to y. So phi x equals to phi y implies x equals to y. This means phi is injective. So phi is an injective mapping provided R is also a finite integral domain, right? We have a finite integral domain, which implies this phi mapping has to be bijective, right? Any mapping from a finite set to itself which is injective is also bijective. This implies phi is bijective. So every element is in the range, which implies the one belongs to phi of R, I mean the range, that is range. Hence it has a pre-image. And what is phi x? It is AX, right? This means x is the inverse of A, right? Multiplicative inverse, right? You found an element x such that AX is 1, but that is the inverse. So every non-zero element, since A was arbitrary, we get that every non-zero element has inverse, of course multiplicative inverse, hence R is a field. Okay, any doubt in this? This is a very good proving technique. If you have any doubt, you can ask. Okay, if no doubt, we'll go ahead. So the next question, now since you know that R is an integral domain, what happens to R over X? I mean set of all polynomials with coefficients from R, right? So, proposition, let R be an integral domain, then for any Px, Qx belongs to R over X, the following holds. One, degree, okay, before that maybe R over X is an integral domain. Okay, so if R is an integral domain, this implies Rx is an integral domain. Second thing, degree of polynomial Px into Qx is equals to degree of Px plus degree of Qx. Okay. And third thing, what are the units? Units of Rx are basically units of not equals to R, just units of R. Okay. So this is the resemblance with R and Rx. We'll prove these results. Okay. So let R be an integral domain. What happens to Rx? You take a polynomial P, which is let's say an xn plus an minus 1 xn minus 1 go on till a1x plus a naught. Similarly, you take qx to be what bn x raised to n, I mean degree n, or let's say another degree m. Okay, I mean of course an and bn are non-zero. That's the way you write it. If I do px times qx, okay, I'll get a term an bm x raised to n plus m and then something, right? So since an non-zero, bm non-zero, this is non-zero term, which implies degree of px into qx is what? N plus m, right? Because you have the highest degree term is n plus m, which is non-zero, and this is same as degree of p plus degree of q. This will give you part 2. Also, see, if p and q are non-zero, then there exists some highest degree coefficients which are non-zero, right? If p and q are non-zero, and I'm getting the product also non-zero because this one coefficient is non-zero. So hence automatically I also get that Rx in the integral domain, right? Because non-zero terms cannot give me a zero term by multiplying itself, right? If I started with two non-zero polynomials p and q, I cannot get a zero polynomial by multiplying those two polynomials. This is what integral domain means, right? Now here also, if you see, if I say if p is unit, then I mean there exists a g or a q such that pq is the constant one polynomial, right? I mean the constant one. What will this imply? By the product you have seen here, this an times bm should be 1, right? Not 1, this should be 0, right? But this implies both an should be 0 or bm should be 0, right? Because you are in the integral domain, right? So this happens for every index. This happens for every index I except for the constant one. And this will imply p is a constant, which will imply p is unit in R. Okay, you started with a unit in Rx, you got a unit in R. So the only units in Rx are the units in R. So from here you get the third one also. You have so many questions. Okay. Now I don't know if matrix rings has been introduced in the lectures yet. Can anyone tell me if matrix rings have been introduced? Okay, if not, I will just explain once. See, you have the matrices, right? Matrices. What is Mn over R? This is set of all, I mean, kind of matrices, n cross n, with entries from the real field, right? So similarly, you can define Mn over this R, which is set of all n by n matrices with entries from given ring R. Okay, this ring can be anything. This can be any ring. Okay, so then the question is, show that for any n greater equal to Mn over R is not commutative. Okay. So provided R is the ring, a non-zero ring, non-trivial ring. So how to show this? Not commutative means I have to explicitly find the two elements whose product is not the same, right? AB is not equals to BA. So let A is E1, 2, which is the matrix can be of any size n cross n. Only the first row, second column is 1, rest all 0. This 0, okay? And then take B as the matrix E21, which is second row, the first row is all 0, second row, first column is 1, all 0. What is this 1? 1 is the multiplicative identity of your ring R, okay? Rest all 0. So what happens if you do AB? So naturally this is a well-known notion, you can verify. E12, E21 is E11, right? Which is the matrix 1 in the first entry, all other are 0. What is BA? It is E21, E12, which is E22. You can verify this multiplication. So this will be 0, 0 and 1 in the second entry, all others are 0. So you can see E11 is not same as E22, right? So always you can find A and B such that AB is not equals to BA. That means no matter what ring you are choosing, if even if commutative, non-commutative doesn't matter. That means Mn over R is always a non-commutative ring. Okay. So you have so many questions today to work out. So do you have, if you have any doubt in any of the questions so far, you can ask. So this was the week 1. If you have no doubts at all, today's session is finished. You can leave. Thank you. You can give feedback or suggestions also, like what questions or what you want more or something, which theory you want to be explained more properly or something like this. Any suggestions?